What's up, guys? So today we're going to solve the B4 Putnam of 2004, and it's a coordinate geometry problem. It's a pretty straightforward one too because it kind of simplifies nicely. So the problem is, let n be a positive integer, n greater than or equal to 2, and put theta equals 2 pi over n. Define points p sub k equals k0 in the xy plane for k equals 1, 2, all the way up to n. Let R sub k be the map that rotates a plane counterclockwise by the angles theta about the point P sub k. Let R denote the map obtained by applying in order R sub 1, then R sub 2, then R sub n. For an arbitrary point, xy, find and simplify the coordinates of Rxy. So, we're going to represent xy in complex numbers because then it'd be easier to deal with the rotation. So if you write u equals x plus yi, the first thing we're going to note is that if you have a complex number z and you want to rotate it counterclockwise by the origin by theta radians, then all you need to do is just multiply it by e to the I theta. So then this works out really nicely because you can generalize it kind of. If you want to rotate it instead of the origin about some arbitrary point k or complex number, you take z, subtract k, and then multiply by e to the I theta, and then you add k because you want k to be the center of origin to rotate it, so you subtract k, and then you want to move back k to its original position. So that's why you do this operation. So we're going to apply the transformation R sub 1. We multiply counterclockwise about each of the specified points in the problem by e to the 2 pi I over n. And we're actually just going to write this quantity out just to make it easier. So a equals e to the 2 pi I over n. Now, we're going to apply the transformation R sub 1, which is about the point 1, 0. So we just subtract 1, and then multiply by a, and then you add back 1, which should equal u times a minus a plus 1. So yeah, there's nothing special about that. So then, if we move everything here, right, then if we apply the transformation R sub 2, we should obtain that this would make the point now equivalent to this quantity, which when you simplify it, it turns out to equal u times a squared, so u times a squared minus a squared minus a, and then you add 2. So if I remove this thing down here, so you can see some kind of a pattern here, because actually if you apply the transformations R sub 1, R sub 2, all the way up to R sub k, you obtain that the the new point should equal u times a to the k minus a to the k minus a to the k minus 1, all the way down to minus a plus k. And this can easily be proven by some straightforward induction. So then this means that after applying the transformations R sub 1, R sub 2, all the way up to R sub n, our point will equal u times a to the n, which is actually just 1, uh, and then minus a to the n minus a to the n minus 1, all the way down to minus a, and then you add n. So this actual quantity equals 0 because we have that this polynomial has all of the zeros which are roots of unity besides 1, because if you multiply this by x minus 1, you get the polynomial x to the n minus 1, which contains all the same zeros, including 1 that time. So you're just removing 1 from the polynomial x to the n minus 1 as a 0. So if you plug in a, then this whole thing equals 0. So this thing right over here, the minus a to the n minus a to the n minus 1, and so on, is actually just this evaluated at a multiplied by minus a. So then that's just 0. So then our whole expression is simply just u plus n, or in other words, it equals x plus n plus yi, which means that our transformation was just shifting the original point through the x-axis by n to the right, x to the n, and then y. Hold on. So yeah, that's the end of the problem. Thanks for watching.